my name is Laura Gomez-Rey, and this is my Physics 2211 lab report on constant velocity. So to start off with, there are some terms that we need to know beforehand. So starting off with Newton's first law states that an object at rest will stay at rest, and an object in motion is going to stay in motion at a constant speed unless there is an unbalanced force added, like done upon it. So with Newton's second law, we see that it's kind of a formula. It's force is equal to mass times acceleration. With net force, it kind of plays along with Newton's second law as it is all the forces that were calculated added together. And then with constant velocity, it means that there is no acceleration and there is no net force. So some formulas that we're going to need for the experiment are the position update formula, which is the position final equal to the position initial plus v average times delta t. And this is what I used to find v average because I already knew the change in time and the initial and final position. And then this is going to help me with the velocity update formula, which helped me find the final velocity of the experiment, which we're going to need to calculate constant velocity at the end of it. And then Newton's second law, which I stated before, is force is equal to mass times acceleration. And then one thing that I want to kind of state is how constant velocity works or what it is. So in this example, we see that we have the force of gravity facing down, which would be negative, and the force above, which is going to be positive. But they are the same force, just opposite from each other. So one is negative. So once they're added together, it's going to equal to zero, which is a total of zero net force, which is why we have a constant velocity. So for the tracker model below, this kind of tracked the experiment that we did. And here's the experiment. You kind of see my finger moving it initially, and then the exo marker goes at a constant speed after that, which is why the graph is linear. So yes, that's why it shows linear. And then we're going to see that it's in a constant velocity after that. Sorry. Okay. And then for the glow stroke code, this is the coded part of the experiment. So this is done by a computer, which kind of shows the experiment with no air force taken into consideration or any resistance or friction. So for the initial position, we put 0, 0, 0, and then the initial velocity, I calculated it using the velocity update formula. So we see here that I changed the velocity and I put the time that it took. So it is at the same velocity that my experiment started at and at the same time it ended at. So it could be the same thing, but this one will have different results. And I put my coding code above. So the calculated analysis, you see that the position versus time is at a linear, and so is the velocity. It's in a straight line, which shows that there is constant velocity because the velocity graph isn't changing. And also you can see here that the position is a little bit higher calculated than the experimental one because, again, the coding does not take into account any resistance that there might be in the air. So for the results, our system was the expo marker that was moving, and the surroundings were the universe, like the table or the air. So there was an initial push. I applied the initial force with my finger, but once the expo marker was at a constant speed, it kind of implied that the initial force was applied with the same opposing forces, which is why it kept going at a constant speed and why the graph was linear, and the constant velocity was showing through the graphs as well. So comparing the model versus the experiment, we see here that the model is at a straighter line than the experiment. But as stated before, this is because the model doesn't really take into account any friction or any air that might be in the surrounding areas. But there are two things that stayed the same. We see here that Newton's law, which is the fundamental principles of physics, do not change, which is that an object in motion will stay in motion unless an unbalanced force is acted upon it, and then the conservation law, which conserves the momentum of the object and the energy throughout the experiment. So what if there was an opposite force? So if there was an opposite force, as you can see in the left picture, you see that there's an original force. The original force is positive, but if there was an opposite force, the object would just be going in the negative direction, but the force wouldn't change, just the sign. And if the axis were flipped, the original axis was on the x-axis, which was going to the right as time changed, but if the axis was flipped, now it'd be going down as time changes, but it would still be the same force. Some errors that might be calculated, as stated before, you can see it because of the calculated experiment. We see here that when calculating, there was assumed that no air resistance would be in the air or friction for that case, which is why I showed the arrows. The white one is the object and the red one is the friction and any air resistance. But in reality, having no air resistance or friction is very hard to achieve in experimental. So with that, so what does it mean if we assume that net force is zero? This means that all forces are balanced, resulting in no acceleration. So that means that the net force is equal to zero. And if there's no acceleration, there is no net force, which is why the net force would be equal to zero. And if an initial force is applied to an object and then removed, the object will stay at a constant velocity due to the net force being zero, which goes back to reinforcing the fundamental concept of Newton's law of motion.